So we have another topic under sequential circuits, the state or finite state machine. Finite state machine is a sequential circuit with random next state logic. So it is also a circuit within a state there is also an internal state. So unlike the regular sequential circuit, the state transition and event sequence of a finite state machine do not exhibit a simple pattern. So the state transition is more complicated and the sequence exhibits no simple, no regular pattern as in a counter or in a shift register. The block diagram of a finite state machine is similar to the regular sequential circuit, but its design procedure is different. The application of this finite state machine is for the control of large and complex systems. So we have some terminologies for your finite state machine the same as your sequential circuit. We have also state diagram, which illustrate the form and function of a state machine. It is usually drawn as a circle and arrow diagram. We have a state, a unique configuration of information in a machine. We have also present state. It is a configuration in which the machine is currently in. Then the next state, a state to which the state machine makes the next transition determined by the input present. We have the transition arc, a change from present state to the next state. So in your FSM or finite state machine, we have states labeled by name or symbol. For any given state, there is a finite number of possible next state. One of the possible next state becomes the new present state that is depending on the input present. For the digital system, state changes on the clock cycle. So from this diagram, it can be deduced that if the present state is state C, then the previous state was either state A or C, and the next state must be either C, B, or F. If you have this present state as C, your state C, your previous state will be state A. But this state C has another next state which is B and F, and it goes back to C. So therefore state C can be now your previous state for state B, F, and for C. There are two types of your finite state machine model. We have the Moore machine. It is a sequential circuits where output depends only on the present state, or in other words, outputs are independent of the inputs. So this is the block diagram of our Moore machine. The other one is a Mealy machine. It is a sequential system where output depends on present state and current inputs. So therefore, outputs are function of the present state and inputs. So this is your block diagram of a Mealy machine, where your inputs also control your output logic. We have this example, but this example is not a finite state machine. It is a regular sequential circuits. So we have to design a sequential circuit with input x. If x equals to 0, the sequence is 0, 1, 2, 3, 4, 5, 6, 7, then goes back to 0. And if x equals to 1, we have 0, 7, 6, 5, 4, 3, 2, 1, then back to 0. And we have to use jiggy flip-flops. So we have your state diagram and your state table. So in your state table, we have the present state and next state depending on the value of your input x. So if your input x equals to 0, your state started at 0. It goes to 1, then to 2, then to 3, then to 4, to 5, to 6, then from 6 to 7, then 7 to 0. Then, if your x equals to 1, it goes from 0, 7, 6, 5, 4, 3, 2, then goes to 1, and it goes to 0. So next, we have to arrange your state table where your x is now in the column with your present state. So we have x equals to 0, then we have to copy all the value of your present state, which is when x equals to 0, as well as the next state. If it is from 0, it goes to 1. From 1, it goes to 2. From 2, it goes to 3. And from 3, it goes to 4. And from 4 to 5. Then 5 to 6. 6 to 7. Then 7 to 0. And for your input x equals to 1. From 0, it goes to 7. Then from 1, it goes to 0. Then from 2, it goes to 1. Then from 3, it goes to 2. And from 4, it goes to 3. And from 5 to 4, 6 to 5, and 7 to 6. Third is, we have to construct an excitation table. In your excitation table, we have now the column for the flip-flop we are going to use. We have the present state, next state, then your G key. So since we have three variables in your state, that is the maximum is 7, so we have also 3 flip-flops. Since we use J key, so we have to designate the first J key as A, second will be B, and the third as C. So for your present state at input x equals to 0, we have from present state of your A going to next state of your A, which is 0. Therefore, your JK is 0 on x. Then for B, it goes to 0. So we have 0x, 0 to 1, that is 1x. Next, we have 0 goes to 0, we have 0x. Then 0 goes to 1, that is 1x. Then 1 to 0, x1. 0 to 0, 0x. 1 to 1, that is x0. Then 0 to 1, that is 1x. 0 to 1, that is 1x. Then 1 to 0, x1. Then 1 to 0, x1. 1 to 1, x0. 0 to 0, x0. 0 to 1, 1x. 1 to 1, x0. 0 to 1, 1x. 1 to 0, x1. 1 to 1, x0. 1 to 1, x0. 0 to 1, 1x. Then 1 to 0, x1. Then 1 to 0, x1. 1 to 0, x1. For your input x equals to 1, so we have your first present state going to the next state, at your flip-flop A, that is A, B, and C, that is 0, 0. So the next state is 1, 1, 1. So this is now the combination of your flip-flop G, A, K, A, G, B, K, B, G, C, and P, C. And from 2 to 1, from 3 to 2, from 4 to 3, then 5 to 4, then 6 to 5, then 7 to 6. After this, we are going to get the equation in each input of your flip-flop. So using map method. So for the state equation under GA, so we have to put the value of your G in your map. So we have 1, XX, and we have another 1, then XX. So we can group this by 2. So therefore, we have GE equals to X bar BC or X B bar C bar. For your KA, we have XX, then 1, XXX, then 1. So we have X bar BC or X B bar C bar. For your flip-flop B, we have your first, that is your GB. So we can group that by 4. So therefore, we have X XOR C. For your KB, and we have to group that by 4. So we have also X XOR C. Then for your GC, to group that by 16, so it is equals to 1. For KC, group this by 16, that is equals to 1. So therefore, we have to do now your logic circuit. So this is your state diagram, and this is now your logic circuit. So this is a regular sequential circuit, which exhibit a simple regular transition pattern. So for this example, it is we are using to implement Mealy machine and Moore machine. So the sequence, so as you can see in your problem, we have to design a sequence recognizer with one input X and one output Y. The circuit will output a 1 when the input string X equals to 111 is detected. The circuit is also required to recognize overlapping sequence. So for example, if our X has this value 110, so the sequence output, if this is your sequence 110, so we have output 00. If it is followed by 1, then it is 0, another 1, 0, another 1, then you have an output of 1 because you have a sequence of 3, 1. Then it follows another 1, so your output is 1 because we have to recognize overlapping sequence. So we have still a 111. Then another 1, so we have an output of 1 because we have to recognize an overlap of this 1. Then if it is followed by 0, then therefore your output is 0. Followed by 1, 0 output. If it is 0, another 0 output. So the sequence is 1, 1. You have an output of 1. So we have this solution. We have to make your sequence not correct as A. If it receives a 1, then it goes to B. And if it receives 1, 1, it goes to C. And if it receives 1, 1, 1, it goes to D. So for the Mealy machine, we have this state diagram. We have A as our starting state. If it receives a 1, so therefore an output is 0, it goes to B. And if it receives a 1, output this time is also 0, it goes to C. And if it receives another 1, this time your output is 1 because you have now 3, 1, 1 in your sequence. It goes to D. So back to your state A. So there is a possibility that your sequence started at 0. So it will go back to your state A. Output for that one is 0. At B, there is a possibility that after it receives a 1, a next state or next sequence is equals to 0. So it goes back to A. Your output is also 0. For C, there is also a possibility that the next sequence after receiving a 1 is 0. So it will goes to A with an output of 0. Then for D, if it receives a sequence after, if his next state is 0 after receiving a sequence of 1, goes back to A with output 0. How about it receive or it has a next state of 1? So it will go back to his state with an output of 1. So we have to put this diagram into a state table. We have your state, we have your input x. If input x is 0, from A it goes to A with output 0. From B it goes to A with output 0. Then from C it goes to A with output 0. Then from D it goes to A with output 0. That is if x equals to 0. If x equals to 1, from A it goes to B with output 0. From B it goes to C with output 0. Then from C it goes to D with output 1. And from D it goes to D with output 1. So as you can observe in your state table, C and D has the same state for x equals to 0 and x equals to 1. So we can reduce this state because C is equals to D. So we can have this reduced table or diagram as A goes to B, goes to C, then C back to C when your x equals to 1. Otherwise, it goes back to A. So your state table will be now x equals to 0, A goes to A, then B goes to A, then C goes to A. For equals to 1, A to B, B to C, C to C with an output of 1. So we have to assign value in your state. So for A, we have to assign 0, 0, B as 0, 1, C as 1, 0. Why we have D? Because if we have 2 bits in your assignment, so the maximum combination of your value in your binary coded decimal is equivalent to 1, 1. So we have to put your D as your last state. So state table, we have the present state, next state, and your output Y. If x equals to 0, we have 0, 0, it goes to 0 with output 0. If it is 1, it goes to 0 with output 0. If it is 2 with is C, it goes to A or 0, 0 with output 0. If it is D or 1, 1, it goes to A with output 0. Now, for 1, if it is 0, it goes to B with output 0. If it is B, it goes to C with output 0. If it is C, it goes to C with output 1. And if it is D, it goes to A with output 0. Now we have to develop our excitation table for your flip-flop JK. So we have to JK, we have to designate this as A and B. So we have your present state and next state. So we have for A to A, that is 0, 0, B to B, that is 0, 0. So we have 0x for both A and B. Then next, we have 0, 0, and 1, 0. So we have 0x and x1. Then we have 1, 0 for A and 0, 0 for B. So we have x1 for A and 0, x for B. Then we have 1, 0, 1, 0, that is x1 and x1. 0, 0 and 0, 1, we have 0x and 1x. 0, 1 and 1, 0, we have x1 and 1x and x1. We have 1, 1 and 0, 0, that is x0 and 0x. 1, 0 and 1, 0, that is x1 and x1. And we have to use your map method to get your state equation. For JE, we have x, x, then 1xx. Group this by 2, so therefore GE is KB. For KA, that is XX, 1, 1, and XX, 1, 0. We have this grouping, that is X bar or B bar, or it can be written as X non B. For B flip-flop, for GB, we have 0x, 0x, then 1x, 0x. So we have to group this. We have XA. And for KB, we have x1, x1, and x1, x1. So therefore, KB is equals to 1. So we have to do, or we have to get your output equation. You have a 1, it is equivalent to XEB bar. Then drawing your circuits. So this is your logic circuits. So your input is connected to your output, that is your Mealy machine. Then for Mealy, we have 0. So in your Mealy, your state has already an output. So at 0, you have an at state A, you have an output of 0. And if it receives a 1, it goes to B with output 0. If it receives another 1, it goes to C with an output 0. And if we receive another 1, it goes to D with an output of 1. If we have 0, as at your state A, it goes back to A. At B, if it is 0, it goes back to A. At C, if it is 0, it goes back to A. And at D, if it is 0, it goes back to A. But at D, if it is equivalent to 1, then it goes back to his state at D. And we have your state table. When x equals to 0, A, it goes to A with an output of 0, B to A, output 0, C to A, output 0, D to A, output 1. Why 1? Because it from your D. So from D, he has an output of 1 going to your A. Then when x equals to 1, A to B, output 0. Then B to C, output 0. Then C to D, your output of C is 0. Then if it is D, it goes back to D with output 1. So we have to assign binary coded decimal of your state. So A is 0, 0 and D is 1, 1. So we have to arrange your state table. We have your present state with your input x, your next state, and your output. So if x equals to 0, we have from 0, it goes to 0. If B, it goes to A. If C, it goes to A. And D, it goes to A with output 1. If it is 1, 1, from 0, it goes to B with output 0. B to C with output 0. Then C to D with output 0. Then D to D with output 1. So we have to create an excitation table. So this is now your combination of your flip-flop that is on your present state against your next state. Then we have to get your state equation for a flip-flop. So we begin with your GE. So that is equivalent to XB for KE. So we have your X bar. For B, solving for your GB, so we have your X and key B. You have your X bar or E bar. For your output Y, you have EB. So doing your logic circuits, so this is your state equation and this is your logic circuits. So if we have to compare your logic circuits of your Mealy and Moore, so this is your Moore. Your Moore has no connection from input to output, where your Mealy, it has a connection from your input going to your output. Output is a function of the present state and input. For more, output is independent of the input. So we have another example. We have to design a sequence recognizer with one input X and output Y. The output will become 1 when the input string is equals to 1001 is detected. The circuit is also required to recognize overlapping sequences. Implement using JK. So first we have to solve using Mealy machine. So we have first state, that is at starting state, it is A. If receive a 1, it goes to B. If receive a 1, 0, it goes to C. 1, 0, 0, it goes to D. So A starting, if receive 1, it goes to B with an output 0. Then if receive 0, another 0, or that is next is 0, it goes to C with output 0. Then if receive another 0, it goes to D with output 0. Then the sequence is 1, 0, 0, 1. And if it receive a 1, it goes to B. So that there will be another overlapping. So we have D to B with output 1. So we have a sequence 1, 0, 0, 1, output 1. If this is 1, then we have 0, 0, 1, output 1. So that is an overlapping. Then at A, if the first sequence is 0, it goes back to state A. Then for B, if the sequence is 1, then it goes back to B. So that if we have 1, 1, then 0, 0, 1, then you have an output of 1. And if C is equals to 1, it goes back to B. And if D is equals to 0, then it goes back to A. So your state table will be this one. If 0, your state A goes to A, your state B to C, your D to D, and your D to E with output 0. And if it is 1, A to B, B to B, then C to B, and D to B. So we have state assignment, then constructing your state table with X and the present state column. We have 0, 0 for your present state or your input X, then from A to A with output 0, from B to C with output 0, then from C to D with output 0, then from D to A with output 0. If your X is 1, from A to B with output 0, from B to B with output 0, then from C to D with output 0, then from D to B with output 1. So we have to construct your excitation table. So we have this 1, 0, 0, 0x, for B 0, 0, that is 0x. Then 0, 1, 1x, 1, 0, x1. 1, 1, x0, then 0, 1, 1x. 1, 0, x1, then 1, 0, x1. Then you have 0, 0, that is 0x, 0, 1, 1x. Then 0, 0, 0x, then 1, 1, x0. 1, 0, that is x1, then 0, 1, 1x. 1, 0, x1, then 1, 1, x0. Then we have to get your state equation. So GE is 1, 1x, then x, x, x. So therefore, we have x bar B. For KB, we have xx, 0, 1, xx, 1, 1. Or that is equivalent to x or B. For your GB and KB, for GB, we have x1, 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 x. So that is x or E. For GB, that is x1, x1, x0, x0. So we have equivalent to x bar. For your output Y, we have XEB. So therefore, your circuit, so your input X is connected to your output. For a more machine, your sequence is 1, 0, 0, 1. So at state A, with output 0, it goes to B when it receives a 1, with output 0 at B. If it receives a 0, it goes to C, with output 0 at C. If it receives another 0, it goes to D with output 0 at D. And it receives a 1, it goes to E with output 1 at E. Then, if your E receives a 0, it goes back to C, because we have, if it is 0, then 1, we have a 0, then 1. So we have a loop of 1, 0, 0, 1. Then if it receives a 1, it goes to B. So we have 1, then 0, 0, 1, output 1. And if it is 0, it goes back to A. And for your C, if it is a 1, it goes back to B. And for B, if it is 1, it goes back to itself. Then for A, goes back when it is 0 by itself. So this is now your state table. We have to assign binary coded decimal for your state. A is 0, 0, then E is 1, 0, 0. So your state table, so since we have 3 variables in your state assignment, that is the maximum is 1, 0, 0. So therefore, we have 8 combination of your present state. So from 0, 0, it goes to 0, output 0. From B, it goes to C, output 0. From C, it goes to D, output 0. From D, it goes to A, output 0. Then from E, it goes to C, output 1. Then, if it is next to E, which is 5, so it goes back to A, output 0. If it is 6, it goes back to A, output 0. If it is 7, it goes back to A, output 0. For your input x equals to 1. At state A, it goes to B, output 0. B to B, output 0. C to B, output 0. Then D to E, output 0. Then E to B, output 1. And for the following combination of your present state, D goes back to A with output 0. And we have to get your state equation. Before we can get your state equation, we have to solve first your excitation table. So this is the combination, your excitation table for your present state going to your next state for the variable E, B, and C. So you have to follow that one. So get the transition from your present state going to next state using your reflux JK. So for the equation, so since it is a 16 combination of your input, so we have 16 square for your map, or we are using 16 square, that is 4 variable map. So this is for your GA. So GA is equals to XBC. Then for KE, so that is equals to 1. Then for GB, is equals to X bar and E X or C. Then key B we have X or E or C. For your GC, E bar B or XB bar. Then for key C, so we have X bar or E or B. And for your output, that is E, B bar, C bar. So your circuits is this one. So your output of your circuit is independent to your input X. So you have to solve for this one. Design a sequence recognizer with input X and one output Y. The circuit will output a 1 when the input string is 101 or 011 is detected. A circuit is also required to recognize overlapping sequence. Then you have to use cheeky flip-flop to implement your circuit design. So that's all for our sequential circuit finite state machine.